Okay, everyone, we're going to continue on with lectures now talking about the QR decomposition. Like I said, we're going to spend 3 days on this. So what we're going to talk about today is sort of an alternative formulation, some of the deeper theory around QR. And then also what we're going to do is continue this on the next lecture, talking about the householder algorithm and how that works. Okay, so QR, and particularly today, we're going to talk about what are called projectors, and essentially a modified Gram-Schmidt formulation of how we're going to find this QR decomposition. Okay, now let's remember from last time. Last time what we talked about is I had a collection of vectors, and n of them, and my data is going to live in an m-dimensional space, and I have n vectors that are sitting in this m-dimensional space. Okay, so that's what this represents, is some this is essentially telling me there's some range which this actually spans an n-dimensional space. And this is going to be essentially the columns of my, these are going to be the columns of my, there we go. Now I'm trying to make sure you guys are all on mute. So if you're not on, just make sure to mute yourself if you're not speaking. Okay, so these are going to be the columns that span this n-dimensional space. They're going to be the columns of my vector, of my matrix A. Okay, and the idea is to find an equivalent. I want the equivalent subspace, but now I want to span it with new vectors, Q1 through Q of n, where these are orthonormal. That is the entire goal of essentially the QR decomposition, or if you want to think about it, from Gram-Schmidt. So what Gram-Schmidt does is say, you give me a set of vectors that span an n-dimensional space, and Gram-Schmidt's going to give you some orthonormal vectors that span that same space. And that is what QR is allowing us to do. In particular, there is a linear transformation between these. And the idea behind QR is to say, oh, I know how to go from one to the other. And the transformation is through an upper triangular linear transformation. In other words, we're going to take the vector matrix A, so that's what we're going to start with. And the columns of A are these n vectors I'm talking about. And what we're assuming is that this is full rank. In other words, it's not degenerate. Two of these columns aren't in the same direction. These are linearly independent directions. Okay? So I have some matrix A, and what I want to do is transform it to some matrix Q. Something like this. So I take a transformation from this n-dimensional column space to this n-dimensional column space, and the advantages become very clear because this space here are orthonormal vectors. Okay, so that's what I want. And how do I do it? Well, you do it through a linear transformation, and you say A is equal to Q R, and R is my linear transformation. Okay, and what we did last lecture is we showed that through Gram-Schmidt, we could actually get this linear transformation. We had an algorithmic way to go about and produce that transformation. And that vector was upper triangular. Of this form. Okay? And what we did for getting this vector is we started recursively. We pulled out the first vector, and then said, okay, that's one direction that we want to go in. And it said, what about the second direction? How about if we look at an orthogonal vector, at a vector that's orthogonal to this direction, get the second direction? How about the third direction? Well, pick a direction that's orthogonal to the first two, and then to the first three, and then to the first four. And the way we did that was by computing these Rij's, which were equal to the projection of each of these vectors onto the qth I direction. Okay, so we were able to show this, and then what we did, we also took this thing and we normalized it. So the normalization also comes in here. Okay, so what we did, we found a way to project this out, and I just want to give one example of it in like a vector geometric way to think about it, and then we're going to continue on this idea. In particular, if I have a given direction, suppose that this is the direction of the vector A1. Okay? So I start off in that direction. I say, okay, I have the first direction. And the way that Gram-Schmidt works and says, okay, you have this direction. The first thing you're going to do is say, the algorithm says, all right, pick that as your first direction. Now, to make it orthonormal, you have to pick a vector in this direction, but that's unit length. Okay, let's say that the unit length vector is this one right here, Q1. So I've got my first direction. Now what I want to do is say, well, okay, how do I get my next direction? Well, suppose the vector A2 is in this direction right here. So what I want to do now to pick the second direction is take this A2 and take the component of A2 that's orthogonal to what I already had. Okay? So in other words, if I think about what is the projection of A2 onto this first direction I have, then I could project A2 onto Q1. In fact, that's exactly what this formula is right here. Right? That formula tells you to take, if you want to find this projection, you take Q1 star dot A2. That is this vector right there. And you know what you do with this vector? You subtract it from A2. So if I were to take this vector right here, oh, we're going to do colors. Okay. I've got a whole bunch of colors. So that's this vector right here. And what I'm going to do with that vector is subtract it from A2. So if I subtract it from A2, it's that vector, which then gives me the direction I want. Okay, that's the direction I want, and then I want to normalize it to unit length. So let's say that's the unit length, that's Q2. So it's sort of as simple as that. That is what Gram-Schmidt is doing. You take your first direction, say that's the first direction, make it normalized to unit length, and then since I have the A2 direction, I subtract the projection along the A1 direction to get this vector, which is now orthogonal to the Q1. So now I have these two, and you just continue this process. So now when you go pick, if you're in three-dimensional space and you want to get Q3, you say, all right, take the A3 vector and subtract its projection onto Q1 and Q2, because then it will be orthogonal to them. So that is the generic formula. That's exactly what we have here. Is the way to do this is through subtracting those contributions of a vector that already are in the subspace spanned by the previous orthonormal vectors. Okay? So that's the picture that we want to have in our mind. All right, so this is where this idea of projectors is going to play a role for us, because what we'd really like to do is, Gram-Schmidt is a nice way to do it. We would like to figure out a nice way to represent this more broadly mathematically in terms of matrix manipulations. And so that's what we're going to do now. All right, so let me erase this, but that's the picture you want to keep in your mind about everything we're doing. Okay. So let's start considering what the idea of a projector is. So first of all, we're going to come back and start to consider this matrix here that we're working with all the time now. Okay. And these columns form an orthonormal basis in some m-dimensional space. Remember, the matrix A itself that I got this from was in some m by n, where m was bigger than or equal to n. Okay? So typically this matrix is, it's tall and skinny. Okay? All right. So now what I want to do and think about with this is that I have this spanning set. And what I want to start thinking about is if I wanted to represent a generic matrix X, vector. So here's some vector X. Generic vector that sits essentially, it's some m by 1. So there's a vector in the m-dimensional space. And the question is, how would I represent this vector in terms of Q, a space that spans n dimensions there, plus something else? So let me show you what this looks like. So the way to generically represent X given this Q matrix is something like this. X is equal to R plus J equals 1 to N QJ star dot X QJ. So what is this object here? This is really important for us to learn because we're going to use this all the time in what we're doing here with our projectors. I have an m-dimensional object and I want to represent it in this using this n-dimensional orthogonal space. But of course, the n-dimensional space, because m is bigger than n, doesn't necessarily allow me to span all m dimensions. So what this, though, gives me is it breaks the vector X into two components. One is this part here. This spans the column space of Q. In other words, whatever the column space is here, this orthonormal set spans, that's what this thing is here. In other words, you take the vector X and you project it into each of these directions, each of the Q1 through Q of n directions. Okay, this is exactly what we learned from Gram-Schmidt. What about this R? Well, the R is orthogonal to the span of Q. In other words, this is out of the range of this set here, of this spanning set, okay, of this space. So R is sitting in the space that's orthogonal to all your Q vectors, and this R spans the rest of that space, which is, if this is m-dimensional, and this is m-dimensional, right, then this is the m minus n dimensions that you have left over. And that's what this R is the representation of X onto the space that's not spanned by this X. Another way to think about this is that this gives us a mapping here onto the n-dimensional space okay, this component here, this is a mapping onto this n-dimensional subspace, or one way to say it is this gives us a projector to the range of P. Okay, range of Q, sorry. All right. So this object, if I take this Q, or this object here, this gives me a way to compute. You give me any vector, and what this object will do is it will project onto the subspace that is defined by Q. Okay? So that's what this thing is. It's this projector into this space. So I'm not just looking at projecting to one direction. I'm looking at projecting into this n-dimensional subspace that's spanned by Q. And this is the object that does it. Okay, so this is going to be an important concept for us to start to develop, because we're going to use these projector ideas all the time. In fact, most of linear algebra, especially as we start building out, we're going to start, even when you look at the SVD, when you do the SVD last time, what we said is you can decompose it into 3 matrices, and then you project, for instance, into these low-rank subspaces spanned by U. Here, the low-rank subspace is spanned by Q. Everything is about projection. When we're dealing with big matrices, especially, we want to project into some low-rank subspaces often to do our computations. And this is just a formal way to start talking about projectors into subspaces, which are objects like this. Okay, let's keep building on this idea. But this is a really important concept, right? I take my m-dimensional space, and if I project it into my representation here, where I have some n-dimensional subspace, well, you project it into the n-dimensional subspace, this is everything else. Okay, this is out of the range of this operation. Okay, or I'm going to talk about this in terms of a null space in a minute. Okay, let's keep moving on. So we have this concept of this Q, and you can see the orthonormal portions of this are allowing us to do some important manipulations. All right, so I'm going to take a vector, and I want to know from that vector, I want a vector y that's in the range of this matrix. So sorry. That's it. Yeah, so it's in the range of this Q. And so I can say, you know, the component of some vector that's in this range is I could take some vector x, and I can say y is equal to, let me write that formula again. Here it was. All I did is I project some vector x. And so the vector x actually can be outside of the range of this, but if I project here, y is the portion of x that sits in the subspace, and that might be the subspace of interest to you or to me, okay? And that's how you get at it. Now what I'm going to do is rewrite this a little bit. The reason I'm going to rewrite this is I can take instead the q of j to the other side, and I have q of j star dot x. And the reason I'm going to rewrite it this way is that what I can actually do is this is going to essentially create for me sort of an outer product structure where I'm going to write this whole thing as y is equal to q star x, where that's what q is. It's the matrix. So remember, this is a sum over all n of them. And instead of writing the sum, I can write this in a more compact form like this. So QQ star becomes this projector. I just take this matrix of Q to Q of n, multiply by Q star, and what I have now is this object is my projector onto the n-dimensional subspace. So take any vector, multiply by this, now you have the projection into that subspace. Graphically, this looks like the following. There's y. Maybe here's q star times x. So this is a decomposition or a factorization into its orthogonal projectors. By the way, you don't have to have an orthogonal projector. I'll talk a little bit more about that later, but mostly we want to be working with is orthogonal projectors. And orthogonal projectors are such that, you know, essentially what we have in a QR, which is orthonormal vectors. Okay? So QQ star is this very important object, and it's going to play a big role in what we want to build in essentially modifying that Gram-Schmidt, because now this thing here just says, oh, if you construct this, I can very easily compute for you any vector's projection onto the subspace spanned by Q, by that object. Okay? It's a compact representation of that. We could, of course, work it out in a sequential way, but this is a very nice compact representation. By the way, just like we did before, there's also this idea of a full factorization. And a full factorization would, instead of looking like this, it would look like, there's your Y. These would be square matrices, Y, Q, Q star, X. Remember before, we thought of these as the silent columns, right, that a full Q arc decomposition gives. And you could imagine I could just make up a full decomposition of the space. And so then you would have this as the projector for the entire space. Okay? All right, so this concept of projectors plays a big role here. And like I said, this is just exactly what we saw from Gram-Schmidt and exactly what we saw from that vector diagram. Subtract off the components that you already have in so that you can build it in an orthogonal direction. And so this projection of the vector onto the Q values are exactly how you do the subtraction process. And so you see this popping up everywhere. And it's obvious why, because you have to compute out the projections onto what's already there. And this formalism here allows you to sort of say, oh, here's a linear algebra form of this instead of a sum form. You just put them all in a matrix. You're done. Okay? All right. So that's going to be the concept. And so I want to start talking more broadly about properties of projectors and how we're going to use them in sort of thinking about a modified Gram-Schmidt's approach. So I'll erase these. I like these pictures, by the way, because we've been drawing them for the SVD, we've been drawing them for QR, we've been drawing here as projectors, and so it's a good way for you to start thinking about linear algebra manipulations, and in particular matrix computations, and that's of course why this applied linear algebra course exists. It's all about how do you put this in terms of linear algebra operations to compute things like this Gram-Schmidt. Okay, so let's talk about projectors or properties of projectors. So a projector satisfies the following property. P squared is equal to P, where we're going to consider y, some vector y, for instance, that's in the range of P in a moment. But the idea is to think about taking this projector that has this property. And by the way, there's two types of projectors you can think of. You could have orthogonal projectors. And the orthogonal projectors are kind of what we've been working with QR, which are orthonormal vectors along each column. But they don't have to be orthonormal. And if that's not the case and you don't have orthogonality, then you have what's called an oblique projector. Okay, but mostly we're going to work with is orthogonal projectors. That's what we're really aiming towards in the QR decomposition and elsewhere. I mean, here's the fact of the matter. If you can get orthogonality in your system, you should always try to do it. Okay, orthogonality just has amazing properties, and you want to basically take advantage of orthogonality in all these computations. So that's what we're really aiming for here is to make use of that. Okay, so let's go take this projector and let's go hit that matrix Y. The vector Y. And the vector Y is in the range of P. So then, P of Y, and in fact, actually what I want to do, before I do that, I want to think about some Y is equal to P of X. So I'm going to go hit some vector X, and it's going to get me to Y. So this is like a linear, I'm going to think of the projector as a linear transformation. Take P, hit X, get to Y. So let's talk a little bit about what that means. So now if I take this equation, hit it on both sides by P, I get Py is equal to P squared X. But the property of a projector is that P squared is equal to P. By the way, the simplest projector you can have is identity, right? Because you have that nice property there, okay? But P squared X then is equal to P of X, but P of X is equal to Y, okay? So another way to think about it is the projector, P of Y equals Y has, you can think about this as eigenvalue 1, okay? All right, so that's number one observation. This is what we want a projector to satisfy. Here's a property around that. Property number 2, or observation number 2. Let's consider Py minus Y. And what I'm going to do with this is I'm going to go ahead and take Py minus Y and hit it with the projector P. So that's going to give me P squared Y minus P of Y. P squared is equal to P, so you get Py minus Py is equal to 0. So notice what this means. The projector acting on Py minus Y, or in other words, identity times Y, that's another way to say it. This is the null space of the P matrix. Okay? So let me write that explicitly. Py minus Y is in the null space of P. And the null space are just the vectors that satisfy an operator hitting something equal to 0. So there's the null space. Okay, we're going to make use of that because that's going to be important for us when we start building out these projectors and guaranteeing that when we project down to with these projectors onto a space, everything sits either in the range or anything that's not in there is outside in the null space.
Professor?
Yes.
Can't the second one be inferred from the first one? Or are they essentially the same thing?
Because we define this, they kind of like basically essentially one, I use that property here, right?
Right.
But if I would have said this was this, then that's the same. Same as this too. All these are kind of like saying the same thing.
Okay, thanks.
Yep. Okay, so we have these nice properties of projectors. And by the way, this is all coming right out of, I'm going to type up some of these notes, but they take a while to put together. But Trefethen has these in his lecture notes. The PDF is you can find on the website. Okay.
I have a question.
Yes.
So is P always symmetric or Hermitian, or is it?
No, it can be. In
But
fact,
not necessarily.
orthogonal, if you have an orthogonal projector, it is Hermitian or symmetric.
Mm-hmm.
But if you have an oblique projector, it does not have to have that property.
Mm-hmm. But this definition of P squared being P is basically assuming that it's Hermitian. We can't define like P squared equal to P for non-Hermitian, right?
This doesn't require it to be Hermitian. Okay, so that's a restriction that you don't have to have it be Hermitian.
Okay, thanks.
All right. So in other words, an oblique projector is still satisfying that. All right, so property number 3. Let's call it the complementary. Projector. So the complementary projector is identity minus P. Now, by the way, we already played with this, right? That was the Py minus Y. Essentially, that's I minus P. And so we're also going to show that I minus P is also a projector. And here's how you do it. Consider I minus P squared. Well, multiply this out. You have I squared minus 2P plus P squared. Well, I squared is just I. Minus 2P. P squared, well, since it's a projector, P squared is equal to P. So you get P, and notice this becomes then I minus P, because you have minus 2P plus P minus P. So in other words, the operator squared is equal to the operator. And that was the definition of a projector. So in other words, the complement, I minus P, is also a projector. So if P is a projector, identity minus P is a projector. But here's the important thing about this. We just showed that if you look at Py minus Y, that was in the null space. And what this implies then is the range of I minus P is equal to the null space of P. So that's what we mean by a complement, right? In other words, what does this operator, what does it span? It spans the null space of P. So essentially, 2 orthogonal spaces. So if I want to span an m-dimensional space, I could do the projector on n dimensions. In other words, the operator P, let's say, spans n of those dimensions. What spans the remaining m minus n? I minus P. That's the orthogonal projector. So between them both, I can get everything. P spans part of the space, I minus P spans the rest of it for an n-dimensional space. And we're going to basically make use of this for ourselves in building out a way to do Gram-Schmidts through projectors.
I'm sorry, there's a quick question. Could you specify the dimension for P? Is it n by 1 or n the dimension of I? I'm kind of confused.
Well, P for us before, remember P was, the P we're going to be working with is this. So this is going to be an m by m. If we're working in this space, right, because this is going to be a projector taking us from Y to X. Okay, so Y is m-dimensional, X is m-dimensional, this is m by m.
Okay. And I assume I is n by m as well?
Yes.
Okay.
Okay. One last thing I want to point out, and this goes exactly to that formulation of QQ star, is if I want to do a rank 1 projection, in other words, I want to take something and I'm going to say, look, I want to project everything to a direction that I pick. Let's say I pick a vector Q, and I want to project everything into that direction. How would you do that? Well, the projector into the Qth direction is Q star. So this looks a lot like what we just did with the matrix Q star, but now this is a single vector. And by the way, this is an outer product. This is a multiplication of that vector times that vector, which is going to give me my matrix that you're just talking about. So this is a projector, a rank 1 projector. And so you can take any data and say, I wonder how all of this projects into, you pick a direction, that's what you compute. Now, I could also ask, okay, well, I want a projector into the space orthogonal to that. Then I'm going to represent that by this. Perpendicular to Q, orthogonal to Q. That's equal to then I minus Q star. So there you go. This is what we're doing. So remember, this is the complementary projector to this. So this here will project me into this space. That's where Q star lives, right? Where this is the projector into a certain direction. Or if these were matrices, it would project me into a collection of directions. This is orthogonal to that. Okay, so I've divided space up into things spanned by this, everything else. And we're going to use this fact for building out our Gram-Schmidt now. So by the way, and if these vectors aren't unit length, you just have to normalize them to do this. All right, so now that we have these projector ideas in mind, let me show you how we're going to change the Gram-Schmidt algorithm using projectors to compute this. Now, what's going to be important is that when we start talking about computing solutions to these linear algebra problems, it's one thing that if the solutions look, there's different ways to get this theoretically. Many of those theoretical solutions for finding AX equal to B, you have to actually compute on a computer. And then there's often a big difference in computational speed and accuracy and stability using different algorithms. So even though on paper they all give me the same thing, the actual execution with code matters. Okay? Okay, so let's do Gram-Schmidt now. Now the idea here, remember, was to say, find a linear transformation from some space n-dimensional, from an n-dimensional space spanned by the columns of A to an orthonormal set of n vectors that are Q. And the linear transformation between them is R. So I've got to find R and I've got to find these Qs. So let's talk about, first of all, how would I find the Qs? The way you're going to do it with projectors is the following way. This is an abstraction, but it works. So first of all, you're going to take the projector along the A1 direction, normalized. So this is going to give you your first Q1 vector. Okay? So when you start this algorithm, right, P1 is just the identity. In other words, just project along the A1 direction. You're just going to pick A1 as A1 direction is good for me, so I'll just pick it. Although you could imagine saying, I want the first direction to be something else besides A1, the first column of this, and this would allow you to make it more general. But now, as you proceed, Q2 is equal to projector and all the way to Q of n. Okay, so this is the algorithm. You project into the A1 direction. Now you project here. Notice what you're doing for Q2. This projector has to find me a space that's orthogonal to Q1 and uses your direction of A2. In other words, it's going to do exactly like what we did before. And how am I going to do this? How am I going to build these projectors? Let me write it down. And then I think hopefully you'll see exactly how you do this. So here is the Jth projector. This, where Q of J minus 1 is equal to Q1 all the way to Q of J minus 1. So what this is telling you is something very interesting. Now we're using the full representation of this projector theory to get us what we want. So the Jth projector, in other words, suppose I've computed j-1 directions that are orthogonal. So I've already started to fill up, in other words, my Q of j so far, the first j-1 orthonormal directions. And now I want a new direction orthogonal to all of these. Well, how do you do it? Right there. There's your projector. Identity minus qj-1, qj-1 star. So remember, this projector here gets me into the subspace that's spanned by these j-1 elements. And I minus this is the complement of that. So this puts me in a space that's orthogonal to this space. Okay? It's as simple as that. As you start lining up Q's, you just compute this product, identity minus this. There's your projector. And then you go hit it to the next vector in A. It's pretty clever, right? And then you just normalize it. That's it. That's how you start to recursively build a subspace for yourself. Now, I want to remind you a couple things. This Q of j-1 is a space that's spanned by Q1, Q2, all the way to Q of j-1. Okay? And the P of j, in other words, this is Q of j-1. The P of j is orthogonal to this. So whatever this subspace is, P of j is basically computing a projection that's orthogonal to it, but that still lives in the space A1, A2, all the way through A of n. So in other words, I'm going to compute this projector that is orthogonal to what I had before, but still lives in my range of the A matrices or the A vectors. Okay? So now what I have, essentially, what I've shown you here, is a way, and in fact, this is an improved way, a modified way, using projectors to compute a Gram-Schmidt reduction of a matrix. Okay? Just through this idea of projectors. So this concept here is really powerful. And in general, you can always take a vector and say, I wonder how much of a vector is in a certain direction or another. The idea of a projector will allow you to explicitly compute things that are in the direction you're interested in and orthogonal to the direction you're in, or are you interested in. Okay, so that's what's really nice about these projectors. They're pretty easy to construct. There they are. Okay, this is just telling me I've got a bunch of directions. Give me the direction orthogonal to these, but still lives in my space. That's the projector. All right, so let's talk about the algorithm for actually doing this in practice. It's recursive, just like what we talked about last time. In other words, you're going to start off by picking the vector A1, for instance, and first finding that direction and normalizing, then go to the next direction, and just recursively adding vectors to this. So by the time I get to the P of j operator, what is the P of j operator or projector? Well, it's basically, here's how it's constructed. It is the product of these. And let me just explain it here in a moment. Hopefully it will make sense. The P of Jth projector that I need to compute, that I want to use, is basically a product of the projector orthogonal to Q1, orthogonal to Q2, orthogonal all the way to j-1. So all these projectors that I could compute, say, what I want to do is I want to make sure that P of j is orthogonal to all the spaces, all the Q's that came before this, all the J minus 1 Q's that are before here. So this is what this represents. It better be orthogonal to Q1. It's orthogonal to Q2, all the way to Q of J minus 1. If we start off with something like P1 is equal to the identity. In other words, you start this off with, you start this off with the identity. In other words, A1 is going to be your first direction. Then this whole thing collapses here to saying, okay, then if I want to represent some vector, so this is how I normally start this. Then you'd say, then if you start this, your direction A1 is the Q1 direction. And then you start. And then you start going from there and you start building your projectors. So I'm going to show you how this algorithm works in practice. So it's an iterative scheme. You start off with a given A of J. First step, V1 is this. Now you're going to build this thing out all the way up to this thing here. So P orthogonal to Q of 1, Vj of 1, okay? And how do you compute what's orthogonal to this V of J1? Well, that's pretty easy. That's going to be V of J1 minus Q1 star dot V1 1 Q1. In other words, subtract out the vector that's orthogonal. So this looks very similar to what we had before. You just compute a projection onto the Q1 direction, subtract it out. That gives you now the V of 2. And then you just continue on up the chain. And that's going to allow you to essentially start building up a set of vectors. In fact, the V of J direction, the V of J is equal to just, as you walk this up, you recursively project all the way, all the pieces out one at a time. And after J pieces, that's going to be your vector V of J. And then what you do is you take this and you normalize it. So after normalization, you have Q of J. Okay, so it's a slightly different computation that does exactly what we did in Gram-Schmidt last time. It's just that the actual computations you do, this is actually more stable than what I had showed you on last lecture. And so the stability is something we're going to talk about later as we progress in the class. What are kind of schemes that you want to do in numerical linear algebra, which ones are stable, which ones are more robust. And so this is a better algorithm than we talked about previously. And then we'll talk about householder as well in the next lecture. And so this is just a recursive scheme for building out, from taking your original matrix, finding yourself a orthogonal embedding for that data, and what the linear operator is that connects the two together. Okay, I think we're going to stop there.